You know that feeling when you're typing a message and your phone just knows the next word you're going to use? It feels like some kind of magic, right? Well, it's actually a super fascinating concept in AI called Recurrent Neural Networks, or RNNs for short. Today, we're going to pull back the curtain and unlock how these networks actually learn to remember and how they power the smart tools you use every single day. Yep, that very feeling of your phone finishing your sentences for you, that's all about understanding sequences, and that is the exact problem that RNNs were designed to solve. So let's dive right in.
Okay, so first things first, the challenge of sequences. The reason your phone's predictive text works is because it gets that in language, order is everything. Dog bites man means something totally different from man bites dog. But for a traditional AI model, that idea of order can be, well, tricky.
See, a regular neural network looks at every piece of information on its own, completely isolated. It might see the word bites, but it has no memory, no clue whether man or dog came before it. To really understand things like language or music or even stock market trends, a network needs a sense of time. It needs a concept of the past and the present.
And that brings us to the hero of our story today, recurrent neural networks. These are the models that were built from the ground up to solve this sequence problem. You can think of them as networks that are built with memory.
The real secret sauce of an RNN is this little thing called a loop. Think of it like a feedback loop. When the network processes a new word, it doesn't just look at that word by itself. It also considers a little note from the word it just saw. And it's this note that allows information to stick around, forming the very basis of the network's memory.
This diagram is a great way to picture how that loop actually works in practice. So on the left, you've got the compact RNN, but on the right, we've unrolled it so you can see what's happening at each step in time. It takes the first input, processes it, and then here's the key part. It passes that information along to the next step, right alongside the next input. It's exactly how you read a sentence. You process one word at a time, but you're always remembering the words that came before.
Now, that little note that's being passed between the steps, it has an official name, the hidden state. The easiest way to think about it is as the RNN's short-term memory. It's just a constantly updated summary of everything the network has seen so far, which lets it make much more informed predictions about what might come next.
But you know, like any good story, there's a plot twist. A basic RNN's memory isn't perfect. Actually, it has a pretty big weakness, especially when it's trying to deal with really long sequences.
We can call this the amnesia problem, and it's exactly what it sounds like. The further the network gets into a long sentence or a long piece of music, the harder it is for it to remember what happened way back at the beginning. The technical name for this amnesia problem is the vanishing gradient problem. Basically, as that note, that hidden state, gets passed from step to step to step, it gets weaker and weaker. By the time the network gets to the end of a long paragraph, the information from the first sentence is almost completely gone. It's like trying to remember the first chapter of a book when you're already on the last page. It all gets a bit fuzzy.
So this is where a major upgrade comes in. To solve this whole amnesia problem, researchers developed a much more sophisticated type of RNN, one with a way smarter memory system. Meet the LSTM. And honestly, this right here, this is the breakthrough that made things like real-time translation and the sophisticated chatbots we have today even possible.
LSTM stands for long short-term memory. And the key innovation, the whole game changer, is a system of gates inside each network cell. So what are these gates? Well, they're like little bouncers or gatekeepers that carefully control the memory. They get to decide exactly what information is allowed to pass through, what gets updated, and what gets thrown out completely.
Okay, I know what you're thinking. This diagram looks complicated, but let's break it down. Don't worry about all the symbols or the math for now. Just focus on that main line running across the top. Think of that as the conveyor belt of the cell's memory. Now those three structures below it, those are our gates. They act like control points, deciding what information gets to stay on the conveyor belt, what gets tossed off, and what new info gets added. It's just a much more sophisticated way of managing the network's memory.
So here's how those three gates work together. First, the forget gate looks at the old memory and decides if any of it is no longer relevant. Then, the input gate looks at the new information coming in and decides what's important enough to actually store. And finally, the output gate figures out what information to actually pass on to the next step in the sequence. This whole process lets the LSTM hold on to a much more useful and long-lasting memory.
Now here's a really cool trick to make your LSTM even smarter. You can make it bidirectional.
This literally means one LSTM reads the sentence forwards, and a second one reads it backwards at the same time. Why is that useful? Well, think about a sentence like, "The movie was not good." If you only read it forwards, you might think it's a positive review right up until you hit the word "not." But by reading it backwards too, the model gets the full context much, much earlier, and that can seriously improve its understanding.
All right, enough theory. Let's see how all of this translates into the actual code you'll be using in your workshop. You might be surprised by just how simple it is to implement these really powerful ideas.
So we'll be using a popular library called Keras, which makes building these networks a whole lot easier. You know that super complex LSTM cell we just looked at with all its gates? Well, in Keras, you can add it to your model with just this one single line of code. Yep, all of that power, all that complexity is packed into one simple command.
And remember that pro tip, the bidirectional LSTM? Keras makes that ridiculously simple too. You just wrap your LSTM layer in a bidirectional layer, just like you see here. With that one little change, you're telling your model to read the sequence both forwards and backwards, giving it a much deeper understanding of the context.
And finally, after you've built all the layers of your network, you have to compile it. This is where you give the model its learning instructions. You define a loss function, which is basically how the model measures how wrong its predictions are, and an optimizer, which is the strategy it uses to correct those errors. It's kind of like giving your model a way to grade its own tests and a study plan for how to do better next time. Okay, we've covered a ton of ground, from the basic idea of memory and networks all the way to these powerful LSTM cells and even how to code them up. Now, let's talk about how you're going to put all of this into practice.
So why does all this matter? Because RNNs and LSTMs are literally everywhere. They're what allows Siri and Alexa to understand your commands. They power Google Translate. They're used to analyze customer reviews to figure out if they're positive or negative, and they even help forecast stock prices. What you're learning today is right at the core of so much modern AI. And now, it's your turn. You'll be training your very own model to write poetry by predicting the next word in a sequence. As you're working on it, think about everything we've talked about today. How could you adjust your model to make it a better poet? Maybe you could use a bidirectional LSTM? Or maybe stack multiple LSTM layers on top of each other. There's a lot to experiment with, so have fun with it. And I absolutely can't wait to see what you create. Good luck.